Hi, my name is Erica Nagy, and today we will be talking about the Unit 2 presentation on genetic mapping. So let me just turn myself to a small screen here. All right. So again, we'll be talking about mapping today of a specific genetic data set. So in mapping, we use three-point mapping actually, so it looks at no crossover events, single crossover events, and double crossover events. So no crossover events are very high frequency in nature, so those are the most usual type of event that we will see, and that involves no exchange of genetic material. For single crossover events, we only see a single exchange of genetic material between two non-sister chromatids. And in this case, we can use single crossover events to look at the linkage between two genes. And in double crossover events, we see very low frequency. So we don't see these very often. It's double exchange of genetic material, and these can determine the linkage between three genes. So the illustrations that we see here are really just showing us what those chromosomes, so to speak, or what that genetic material will look like. It gives us a good visualization of these crossover events. So in no crossover, we see that it's just all one strand of genetic material. In single crossover events, we see these single exchanges of the genetic material. And in double crossover events, we see these double exchanges of the genetic material. Over here on the right is the subset that we will be analyzing today. And you can see the different frequencies of offspring next to that data set. So when we're analyzing the data set, we're looking for non-crossover events, which again are our highest frequency. So here we can see at the top, we have our non-crossover events. Again, that's no exchange of genetic material. And we see 1,340 and 1,362. So those are our frequencies for the non-crossover events. Our two double crossover events are of our lowest frequency. So that's frequency 100 and frequency 140. Now, I know it looks a little different over here in our visualization of those events. Oops, let me go back here. So it doesn't look like a double crossover event, right? It looks like a single crossover event, but that's because the order of these genes isn't correct. So that's important to keep in mind because we'll touch on that later. And then we see single crossover events, and there are 4 of those. So there's 400 frequency and 420 frequency, and that's one set. And then there's 970 frequency and 1010 frequency. So to look for the map distance between B and A, we have to remember those genes aren't exactly in order, and we'll touch on that next. But we do is we take our single crossover events and add those, or that first set between B and A, to our double crossover events. Divide that by the total organisms or offspring that we see, which is 5,742, and we got that number from our total frequencies off on the side. And then we multiply that by 100. So the map distance that we get between B and A is 18.46 centimorgans, or map units. The map distance that we get between A and C, we take the single crossover events seen between A and C, add those to the double crossover events again that we used for our first map distance, divide that by the total offspring, and then again multiply that 100. So we get our map distance between A and C of 38.66 centimorgans, or map units. For the coefficient of coincidence and the interference, we take our observed double crossovers over our expected double crossovers. So to get our observed double crossovers, we take the double crossover frequency that we had, so that 100 frequency plus 140, we divide that by the total offspring, and then we divide the number that we get from that by our map units that we got in our previous equations, and that gives us 0.59 for our coefficient of coincidence. For our interference, and again, this is the inhibition for crossover events, so our interference tells us the coefficient of how much our crossover events in the future will be inhibited. We take the coefficient of coincidence and subtract that from 1, so our interference is 0.41. So now we have to look at the correct order of the genes. So of course, again, before we saw in our single crossovers, some of them look like double crossovers, but they are in fact single crossovers. So we'll start with our correct order of genes. We see BAC as opposed to ABC. So when you take them as BAC, for example, for our single crossover events, when you switch the A and the B, as you can see on the right-hand side here for the 400 frequency. Once that B and that A gene are switched, now it looks like a single crossover event. We have the same thing for our 420. Once you switch B and A, you see A and C next to each other, and then the positive sign on the left-hand side, that looks like a single crossover now. Same thing for our double crossover events. Once you switch the plus sign at the A and the B, you now see a double crossover event. And again, up here, once you switch the A and the plus sign at the B, you see another double crossover event. So this pattern would give us what we expect from the single and double crossovers. And thank you for listening.